Hello everyone. Today we will discuss the design paradigm of algorithms, which is called as divide and conquer. Whenever we have a complex problem, at a stretch solving the complex problem is very difficult. So that is the reason why to solve such type of problems we have one algorithm design paradigm which is called as divide and conquer. The problem is divided into n subsets and each problem is solved independently and then combine the solutions. For example, the design paradigm which is called as divide and conquer. The problem is divided into n subsets and each problem is solved independently and then combine the solutions. For example, so whenever we have a problem P, the problem P is divided into some subproblems P1, P2, P3 and so on Pn, and check whether the problem is solved at this particular stage or not. If it is solved, okay, we can find out the solution of P1. If not, the P1 is further subdivided into subproblems like P11, P12, P13 and so on P1n. Like this, the division is continued until we get a problem which is called as trivial problem. So, trivial in the sense it is easy and simple to find out the solution. So, in divide and conquer, whenever we have a problem of having n inputs and the problem of n inputs is being divided into subproblems and each subproblem is sharing the size of the input. Fine. So, here the subproblems must be solved independently and then we are going to find out the solutions by combining the solutions of the subproblems. So, if the subproblems are still large, and then divide and conquer strategy will be reapplied and solve the subproblem. And we have to take care that the subproblem should be same as the original problem. It should not change the nature of the problem. So, whenever we are having the reapplication of divide and conquer strategy, and this is usually solved or expressed in terms of recursive algorithms. So, for example, let us consider how the divide and conquer will work. Let us see the control abstraction here. So, rather than saying it is algorithm, I am saying control abstraction. So, means that we are describing the working principle of divide and conquer in a general way, in an abstract or in a high level way, by specifying what are the operations we are going to use, but we are not specifying how these operations are going to be implemented. So that is the reason why control abstraction is different from the algorithm. So usually the algorithm will specify what to do as well as how to do, whereas the control abstraction will specify only what to do. It gives only the high level descriptions. So let us start. Algorithm divide and conquer the problem P and check whether the problem P is small or not. If it is small and easy to handle, trivial in nature, then return the solution of P. Else, divide P into smaller instances like P1, P2 and so on Pk. Always my subproblems are k greater than or equal to 1. Because if it is only one subproblem, then there is no question of division. And then apply divide and conquer to each of these subproblems. Fine. And after applying divide and conquer, again each subproblem it checks whether it is small or not. If it is small, find out the solution. If not, the subproblem is further divided into subproblems. Fine. So I am applying divide and conquer for problem P1, problem P2 and so on, problem Pk, and these solutions, each procedure is returning the solution of divide and conquer of solution of problem P1, P2 and so on Pk, and then I am combining the solutions. See, if you observe here, there are three important operations here. One is checking whether the problem is small or not, and the other one is dividing the problem P into subproblems, and then the other one is combining the solution. So here I am mentioning what to do. What is the operation I am going to do, but I'm not mentioning how these check how the problem is small or not, how to check it, and how to divide the P into smaller instances, and how to combine the solutions of the subproblem, we are not mentioning. So there is an important point we need to learn here is nothing but whenever the problem P is divided into some subproblems, sometimes the combination of the solutions, so I'll be getting the solution of P1, solution of P2 and solution of Pk. So sometimes one of the subproblem solution could be the problem of the entire problem, or the union of the solutions of all the subproblems could be the solution of the original problem. So it depends on the problem nature which we are applying. So let us learn which type will be giving like which problem I need to consider the combined solutions or individual subproblem solution. So this is what divide and conquer control abstraction. As I already said, so this is what, so small p is a Boolean valued function. So it returns the solution where if the problem is small enough or not, and p is divided into smaller subproblems P1, P2 and so on Pk, and combine is a function that determines the solution to problem P using k subproblems. And if the size of P is n and the sizes of the subproblem is k, k subproblems is n1, n2 and so on nk, then the computing time of this subproblems, finding the subproblem solution is usually mentioned in terms of the recurrence relation. So how it is mentioned is nothing but, so let us consider T of n is the time complexity to find out the solution of the entire problem, and if n is small means the problem is very simple in nature, which is equal to g of n. Usually this can be represented as a constant value. If not, if n is large, n is greater than, maybe the input sizes may be large in the sense greater than or equal to 1, or sometimes it may be 0, right? So then in such case, the time required to solve the subproblem P1 of size n1 and P2 of size n2, and the time required to solve Pn, the subproblem Pn, the subproblem Pn of size n. So where T of n is the time of divide and conquer of any input size n, and G of n is the time compute the answer directly if we are having the small inputs. F of n is a function where here we get the solutions of independent subproblems. So I required some time to combine the solutions of the independent problems. So this f of n is used to is the time required to combine the solutions of the subproblems. So the time complexity of this particular divide and conquer algorithms usually represented by recurrence relations, because we are having the problem, the subproblem which is of same as the original problem. So I can call the same solution but varying the size of the input. So here I can generalize the divide and conquer time complexity equation. T of n is equal to T of 1 because it is a constant when n is 1. If not, so I may have a number of subproblems. So a is representing the number of subproblems, because I am having in the earlier case I have 1 to k number of subproblems, and each subproblem is sharing the size of the input. Sometimes the problem P is divided into two subproblems P1, P2, and here if it is P is having input size n, then P1 may be having of input size of n by 2, and this may have a size of n by 2. If further it is being reduced, then P11, P12, n by 2 is still reduced to n by 4, and so on. So hence how much input size is being shared. So this B is nothing but the share of the input for each of the subproblem. So usually the B value is in terms of the powers of 2. So for example, so if I am having, usually the B value will be having the powers of 2 depending on the k number of subproblems. And of course, after getting the independent subproblem solution, I need to combine the solution which is equal to f of n. Fine. So hence the time complexity T of n for any divide and conquer strategy problem is A into T of n by B plus f of n, where A is the number of subproblems and T of n by B. N by B is the how much input is being shared by each subproblem, and then f of n is the time required to combine the solutions of the subproblems to get the entire problem solution. Let us consider an example. Consider the case in which A is equal to 2. So which means that the number of subproblems I am having, two subproblems, and B is equal to 2. Every time the input is being reduced by 2. So, and I am assuming that let T of 1 means whenever I have the input size 1, then the time required to find out the solution is 2 units. And because I am having n inputs, the time required to combine the solutions may also be generally proportional to n. So here I am assuming that f of n is equal to n. So my equation is 2 into T of n by 2 plus n. So if you observe here, this type of relations are called as recurrence relations. So recurrence relations in the sense T of n is expressed in terms of T of n only, provided the input size is being reduced. Now I should replace, now here my T of n is equal to T of n by 2. Now if you observe here in T of n by 2, so consider the original equation. So now I should find out T of n by 2. So which is equal to 2 into, in place of n I am having, so T of n by 2 is equal to, in place of n I am having n by 2. So 2 into T of n by 2 divided by 2, because in place of n I am having n by 2. So plus f of n is again n by 2. So n by 2. So T of n by 2 is equal to 2 into T of n by 2 plus n by 2. So if you observe this entire square braces is the term for T of n by 2. So 2 into T of n by 2 plus n by 2 plus n. Fine. Now observe here. So simplify the equation. So 2 into 2, it becomes 4T by 4 plus 2n, because 2 gets cancelled and plus n, it becomes 2n. Now observe here, in place of n I am having n by 4. So how it will be? So T of n, now in place of n I am having n by 4. So T of n equation is equal to 2 into T of n by 2. N by 2 is same, but in place of n I am having n by 4 plus n by 4. So this becomes 2 into T of n by 8 plus n by 4. So observe here, I am writing in for this entire term I am writing 2 into T of n by 8 plus n by 4, and remaining terms will be as it is, will come as it is. So it becomes 8 into, simplify, it becomes 8 into T of n by 8 plus 3n. So if you observe here, this equation I can write it as 2 cube into T of n by 2 cube plus 3 into n. So I can generalize this. So if I am generalizing this, it becomes T of n is equal to 2 power I T of n by 2 power I plus I into n. So if I told you that n is equal to b power k. So always my number of subproblems are in terms of powers of 2. So here b is 2. So n is equal to 2 power k. So if I want to get my k value, then it becomes log n to the base 2. Log n to the base 2. So hence I can replace. So here k is nothing but I am assuming here I value. So replace this 2 power I. So 2 power log n to the base 2 t into n by 2 power log n to the base 2 plus n log n to the base 2. So if I simplify this, this becomes n power log 2 to the base 2 kada. So this becomes n power log 2 to the base 2 and this becomes constant here. So plus into t of n by n. This becomes n by n. So n gets cancelled. So n into t of 1 plus n log n to the base 2. So hence my equation is t of n is equal to n into t of 1 plus n log n to the base 2. So usually while calculating the time complexities, we will ignore the lower powers. Hence, the time complexity of the divide and conquer problems in general can be expressed as order of n log n to the base 2. Order of n log n to the base 2. So this is how the time complexity is being calculated. So this is in terms of the recurrence relations. So to find out the time complexity of divide and conquer strategy, I have two kinds of methods. One is called as substituting the recurrence relations. This is the first method, and the second method is using the generalization method. Using the generalization method. So in generalization method, I would not know what is my a value and what is my b value. But I am trying to generalize the equation like this. Let us consider t of n. So this is t of n is equal to a into t of n by b plus f of n. So I am assuming that n is the size of the p and k is the number of subproblems, and here n is expressed in terms of b power k, hence k is equal to log n to the base b. So observe how we have solved the previous recurrence relation. In the same way we are solving this. However, we are trying to get some generalization. So a remains same. So in terms of n, I am having n by b. So I am just replacing that recursively. So this becomes a into t of n by b into n by b divided by b. In place of n, I am having n by b. So f of n becomes f of n by b, and remaining f of n term will be as it is. So this becomes a square t of n by b square plus a into f of n by b plus f of n. Now observe here, in place of n I am having n by b square. So again I need to solve it, replace it recursively. So a into t of n by b square divided by b plus f of n by b square and remaining terms as it is. So now it becomes a cube t of n by b cube and a square into f of n by b square, a into f of n by b plus f of n. So like this I can generalize the equation. I can say that a power k into t of n by b power k plus, if you observe here, so a square f of n by b square and a into f of n by b and so on f of n. So means that here whenever Whenever it is cube, here it is square. So means that if I generalize this particular term, so this will be a power k minus 1 plus f of n by b power k minus 1. However, to reduce the complexity of the equation, I'm assuming that this f of n is being added with k number of times, because k minus 1 times is approximately equal to k times. So hence I am saying that which is equal to, this is being approximated as k into f of n. So I am replacing the k value now. So this becomes a power log n to the base b, and b power k is n here, and k is log n to the base b into f of n. So I am taking the n value as base, n power log a to the base b, and n gets cancelled, it becomes t of 1 and f of 1 into log n to the base b. So here whatever the term I am having, so this is the equation I am having. So from this I am trying to take out the common n power log a to the base b. So t of 1 remains here, and f of n into log n to the base b divided by n power log a to the base b. So this f of n divided by n power log a to the base b I am assuming as h of n. So from this h of n, so h of n into log n to the base b is nothing but k. So k times, if I am taking the h of n value, then I will be getting the un value. So un is equal to sigma. So this I is equal to 1 to k h of b power j. So this entire term I am writing as u of n. So once I got this, I have a table which is establishing the relationships between h of n and u of n. So the equation I left over here is nothing but t of n is equal to n power log a to the base b t of 1 plus u of n. So here we have the established relations between h of n and u of n. If h of n is order of n power r, where r is less than 0, then my u of n is equal to 1. Because h of n is nothing but, we have already got this, if h of n is equal to f of n divided by n power log a to the base b. So similarly, whenever my h of n is equal to log n to the power I, where I is greater than or equal to 0, then my u of n I will be writing as log n to the power I plus 1 divided by I plus 1. So here if you observe here, r is less than 0, maybe greater than or equal to 0, and if it is greater than 0, I'm having three possibilities. So omega of n power r, where r is greater than 0, then I can write u of n is equal to theta of h of n. So let us see an example of these three cases. So let us consider a is equal to 1, b is equal to 2, and f of n is equal to c. So first of all I should calculate my h of n. So h of n is equal to f of n divided by n power log a to the base b. F of n is c here, and n power log 1 to the base 2 is 0, n power 0. So because my power is equal to 0, so higher this h of n I can write it as log n to the power 0. So hence my u of n will become log n to the power 0, 0 plus 1 divided by 0 plus 1, which is equal to log n. So I can substitute this in the t of n function. T of n is equal to n power log a to the base b into t of 1 plus u of 1. So u of 1 is theta log n. So this is nothing but, so this becomes log a to the base b becomes 0, n power 0 1. So this entire term is constant. So hence the time complexity t of n is equal to theta of log n. Theta of log n. So like this I have different examples here. We can solve all these examples. So let us consider a is equal to 2, b is equal to 2, and f of n is equal to cn. So first calculate h of n. H of n is equal to f of n divided by n power log a to the base b. So n power log 2 to the base 2 is equal to 1. So here n gets cancelled, so which is equal to c log n. C only constant, so I can write, because the C is power 0, so n power 0, so I can have, whenever I have power 0, I can write log n to the power 0. So hence u of n is equal to theta of log n. So substitute this in t of n. So t of n is equal to n power log a to the base b t of 1 plus u of n. So anyway, this value is n here, and here I got n log n. So I can ignore the lowest power. So hence the time complexity is theta of log n. So if you observe here, to this function only we have calculated the time complexity using recurrence relation. There also we got the order of n log n to the base 2. So similarly, I can have another example. So where my a is equal to 7, b is equal to 2, and f of n is equal to 18n square. So here f of n 18n square divided by n power log 7 to the base 2. So this value will be 2.81. So 18n square. So n power 2.81 will become n power minus 2.81 if I bring out to the numerator. So this becomes the negative value. Whenever n power r and r is less than 0, my u of n is equal to constant. So substitute the same u of n in the t of n equation. So n power log 7 to the base 2 t of 1, and this entire term will become the constant. So hence the time complexity is equal to n power log 7 to the base 2, which is equal to n power 2.81. So there is a problem which is called as Strassen's matrix multiplication. Usually for matrix multiplication, we will be having the time complexity of order of n cube, but the Strassen's matrix multiplication has reduced the time complexity from n cube to n power 2.81, and the problem can be solved with divide and conquer only. We will see in the next videos. And next, coming to example 4, and here a is equal to 9. The number of subproblems are 9. The input size is being reduced is 3, and f of n is equal to 4n power 6. So calculate h of n, 4n power 6, n by log a to the base b, and 4n it becomes 9 I can write it as 3 square. So log 3 to the base 3 is 3 only, and here this becomes n square, n power 6 by n square, it becomes 4n power 4. And here n power 4 I am having r value, the power value r is greater than 0, hence my u of n is equal to theta of n power 4. So substitute in the t of n equation, n power log 9 to the base b t of 1 plus theta of n power 4. So this becomes n square into n power 4. So hence the time complexity is theta of n power 6. We have seen the 3 different cases. One is r, n power r, where r is less than 0, and other one is equal to 0, and the other one is greater than 0. Fine. So these examples are covering the 3 scenarios. So this is what the divide and conquer. So divide and conquer can be applied to solve many problems. The first problem which is illustrated is binary search, and the other one is finding the minimum and maximum value in a given array, and finding out the defective cell in the chessboard, and two sorting algorithms called as external sorting and the internal sorting. So merge sort is usually called as the external sorting because it is using an auxiliary memory to sort out the given list of elements, and the other one is the in-place sorting or the internal sorting. It just uses the memory whatever we have given as input to sort out the elements without using any temporary memory. So hence quicksort is called as a internal sorting. And the other one is, as is just now mentioned, that Strassen's matrix multiplication. So which is there was a mathematician who proposed this called Strassen. He replaced the expensive multiplication operations by number of additions and subtractions, so that the time complexity can be reduced from n cube to n power 2.81. So these are the problems which can be solved with divide and conquer. So this is the assignment you can take down, and you can try out deriving the time complexities with different a values, b values, and f of n values. You can try out both using the recurrence relations, and followed by the generalization method using h of n and u of n methods. And usually recurrence relations will take much time because it needs a more number of steps, whereas h of 1 and u of n generalization method may require few number of steps, but it is uh, too important to understand the functions of h of n and understand and remember the functions of h of n and u of n. Thank you for watching. If you have any doubts, you can post it on the channel.